Light-emitting diodes have become an ubiquitous and essential part of the modern person's everyday life. Over time, LEDs have been advanced and adapted to help shine light on new technological advances. LEDs produce light via the transfer of an electron from a group 5 element such as nitrogen to a group 3 element such as gallium. The farther that the group 3 and group 5 elements are, the harder it is for them to transfer their electrons. In LEDs, the separation between the elements is such that the energy needed to overcome the activation barrier corresponds to a wavelength within the visible spectrum. The energy difference between the conduction and the valence layer is known as the band gap. In this experiment, we will be measuring the active band gap, which is the energy needed to produce a photon, and the intrinsic band gap, which is the energy needed for electrons to be conducted without the emission of light. In this experiment, we hypothesize that an increase in temperature will decrease the energy needed for conduction to happen. We also hypothesize that a change in the conductivity of the semiconductor will alter the color of the LED. We will look at blue, green, yellow, orange, and red LEDs. To create LEDs with the different colors, the semiconductors can be doped, which is the act of adding a different group 5 or group 3 element to the semiconductor. For gallium nitrogen LEDs, indium is added to make blue and green, and aluminum is added to create red, orange, and yellow colors. We will be able to calculate how much dopant is added to the LEDs by using the experimental active band gap energy values. The LEDs we are using are known as P-type doped LEDs. P-type doped LEDs are where there is an extra layer of group 3 element added just above the valence layer, close enough so where the electrons can tunnel from the indium or aluminum into the gallium layer. Using a UV-Vis spectrophotometer, we are able to measure the emission spectra of the 5 different LEDs. From these spectra, we can measure the wavelength with the most intense emission from each LED, also known as the lambda max. Now that we have the lambda max for each of the different colored LEDs, we will be able to calculate the active band gap energy. Now that we have calculated our experimental active band gap energies, we will be able to find the ratio of indium to gallium in our blue and green LEDs. The process for calculating the ratio of aluminum to gallium in red, orange, and yellow LEDs is very similar. Now that we've calculated the dopant ratios, it can be seen that as more indium is added, a more redshifted or a longer wavelength is observed. And in the aluminum doped LEDs, a more blue shift or smaller wavelength is observed. The next thing we will be calculating is the full width half max for each of the emission spectra. The full width half max is a measurement of how narrow the range of emitted wavelengths are. Here we can see the wavelength values which will be used to calculate the full width half max value for the blue emission spectra. In the next part of the experiment, we will be measuring the intrinsic band gap energy by looking at the potential of the conductor at different temperatures. We will start by submerging a thermometer and the LED into a hot water bath and start collecting at 30 degrees Celsius and finish collecting at 80 degrees Celsius. To calculate the intrinsic band gap energy, we will take our experimental data, which is voltage over temperature on the y-axis and reciprocal temperature on the x-axis, where the slope of the line of best fit for our experimental data is our intrinsic band gap energy. Here we can see an example of our experimental intrinsic band gap energy for our blue LED. Here it can be seen all of the experimental values we've calculated thus far. One interesting thing to note is how much smaller the full width half-max values are for the aluminum-doped LED semiconductors. Finally, we will be measuring the intrinsic band gap energy of a silicon dioxide insulatory standard. For a material to be considered a good conductor, the ratio of the populated states in the conduction band to the valence band should be roughly 1 to 3. Using a Boltzmann distribution equation, we can calculate the populated state ratio using the intrinsic band gap energy of the silicon dioxide standard. With a populated state ratio at 300 degrees Kelvin, or room temperature, of 1 to 100 trillion, it is clear that our standard is a very poor conductor. In order to find what temperature our standard would be considered a good conductor, we can set our Boltzmann distribution equation to 1/3 and then solve for temperature. For our standard, it would need to be 8,900 degrees Kelvin for it to be considered a good conductor. Here we can see our experimentally calculated intrinsic band gap energy data for our silicon dioxide standard, where the slope of the line of the best fit is our intrinsic band gap energy. We can use these Boltzmann distribution equations to surmise what might happen to our LEDs if we change the temperature drastically. When we calculate the conductivity ratio for our LEDs, it can be seen that the value is much smaller at liquid nitrogen temperatures versus room temperature. Another way that this decrease in conductivity of the LED can be thought of is that as the LED is cooled down, its active band gap energy is increased, meaning it will take a larger amount of energy to transition the electron from the conduction layer to the valence layer. Due to the fact that energy and wavelength are inversely proportional, we would expect, as the temperature decreases, there to be a blue shift in the observed color of our LEDs, which is really saying, as the energy of the transition increases, the lambda max decreases. We can test our hypothesis by getting some liquid nitrogen and using it to cool down the LEDs.
That's good.
When submerged in liquid nitrogen, the yellow LED turns green. The orange LED turns yellow. And interestingly, the blue LED loses its color, which I would assume is due to the color being shifted into the invisible ultraviolet spectrum. Through conduction of the experiment, both hypotheses were found to be supported. Thank you for watching. I hope you found this video to be interesting and that you gained a little more appreciation for light-emitting diodes.